Hello everyone, welcome to another interesting class on control system. In today's class, we are going to talk about frequency analysis using Bode plot. What is Bode plot? So, a Bode plot is a graphical illustration of a control system that emphasize on the frequency characterization of your control system. Representing the control. So far we have seen the control system can be represented in the time domain. So that is your C of t, and the control system can be represented in your Laplace transform, that is C of s. And now in this unit we are going to see how we can represent your control system in the frequency characterization, that is the omega. So the omega is your digital frequency. So we are going to see how you can represent control system in the frequency parameter. Good. So that for that we use this Bode plot. So Bode plot is very helpful for representing your control system in the frequency domain analysis. So now you may ask a question, how it is different from a Fourier transform. So we have studied that Fourier transform does the same thing. The Fourier transform takes your signal or a system and it represents it in the frequency domain. Okay? A Bode plot differs from the Fourier mainly because the Bode plot operates on the S domain control system, right? The S plane. So the control systems that are represented using the Laplace transform, the Bode plot can be applied. Whereas your Fourier operates on the time domain, or Fourier operates mostly on the C of t, G of t, H of t. Then the second thing is the Bode plot gives the dB representation. So the Fourier gives the frequency representation, whereas your Bode plot gives that 20 log 10. So that is the dB scale. And the use of dB scale is very advantageous. The semi-log graphs are very advantageous when your frequencies range from say hertz to megahertz. So capturing this in the same graph, it becomes very difficult if you use a linear scale. So if you use a normal scale, it becomes very difficult, but in the semi-log, you can capture a large variations of frequency because one grid is multiple of 10. So that is the semi-log graph we'll be seeing, which we use for the Bode plot. All right, so now we will come to the numerical on the Bode plot. So we are going to see how we can sketch the Bode plot for the given G of S and then obtain gain and phase margin. So what is gain and what is phase margin? I will be covering that in the later part of this numerical. So as you can see here, the step one is to find omega n and the damping ratio. So this is a second order system, as you can see from G of S. It is a second order system and the non-factorizable polynomial, that is s square plus 16s plus 100, that represents your characteristic equation. So the omega n square is taken to be 10, right? It's 100 and where omega n is equal to 10 and my damping ratio is 0.8. All right, so that is how I get the frequencies. Then the step two is make the coefficients constant in the first and the second order equation. So what do we mean by constant coefficients? So what we mean by constant coefficient is the coefficients that are not containing any s terms, s to the power of 0, or I can say that they are the constant coefficients. So here, if you see 1 plus 0.2s, the constant coefficient term is already 1. So I don't have to do much with that. Okay, and then my s square, so the second order system, s square plus 16s plus 100, the constant coefficient term is 100. So I'm going to take the 100 outside. So that's going to come out to be s square by 100 plus 16 by 100 plus 1. So then that is where I make my constant coefficients to be 1. So this is the step 2 in your Bode plot and it is important. So here, like I said, we are not doing this either way. We have just used it as it is because we are not taking that partial fraction expansion. So that is one thing you have to know. In Bode plot, if the question is about G of S, you can directly go ahead and compute this omega n and damping ratio without having to do the partial fraction. And then you can do the step 2, which is making the constant coefficients to be equal to 1 as shown here. Good. So that is my step 2. Once I've completed my step 2, I get the simplified g of s in this form as shown in this box. Now let's get to our step 3, and the step 3 involves the corner frequency. So in Bode plot, we are gonna call something as the corner frequencies, or they are you can say they are the range of frequencies. The frequency ranges in G of S. So which means when I say corner frequency, it just means the transition frequency. So 0.55 means 0.5 is one of the corner frequency and 5 is the next corner frequency, and that is where you have a change of slope. At 0.5 your slope changes, and at 5 the slope changes next. That is why they are called as your corner frequencies. So now let us see what are the frequencies. So the first thing we want to find is, for fixing the corner frequency, we want to find the frequencies that are visible in your G of S. So if you take G of S, you can see that my omega is equal to 1 by zero point 0.2, that is 5, and my omega, the second order system, my omega n is 10. So this is the two frequencies I can fix from G of S. So from my G of S, for the first order system, the frequency is given by 1 divided by the coefficient of S, that is equal to 1 by k, and in this case that is zero point 0.2. The k value is zero point 0.2. So 5 and 10, they are my frequencies from G of S. So these are the frequencies that are already visible to me, and that two frequencies, that 5 and 10, compulsorily becomes my core frequencies. Okay, when I say core frequencies, they are inherent frequencies of the system. They are like the fundamental frequencies of the system. And apart from these 5 and 10, I can take two other frequencies. I'm going to call them as the lower bound frequency and my higher bound frequency. Good, or my upper bound frequencies. So I'm going to choose that to be less than 5 and greater than 10. So I'm going to select pick values of 0.5 and 20. And I need to do this for all the numericals on Bode plot. The steps 1, 2, 3 are, all the steps we are saying are pretty much uniform for all the standard Bode plot problems. There are some numericals which are little indirect for Bode plot computation, which we will be doing in one class. So I'll take one lecture on indirect forms for Bode plot, which is little difficult, but the standard solving for Bode plot is all these steps that we are seeing in today's class. So now we go to the step 4. So after corner frequency measurements, we come to the step 4, which is your Bode slope measurement. So if you see in your Bode slope measurement, you have the pole at first order and you have the pole at second order. Good. So what is pole at first order and what is pole at second order? It just means that if you have a first order system, that first order system contributes a pole of minus 20 dB slope. And if you have a second order system present in your G of S, that second order system contributes to a minus 40 dB slope. Then if you have zeros at first and second order, then they contribute to plus 20 and plus 40 dB. So here the polarity, the sign is of essence. So if you see, for my poles, the sign is negative, minus 20 and minus 40. And for my zeros, the signs are positive, plus 20 and plus 40. Alright, so now what is the rule for coming up with this order? So the next thing is for the Bode slope measurement, you need to write, you need to form an ascending order. You need to write it in ascending order. So the poles at origin and the zeros at origin comes, they take the priority. And after that, the first order. Origin, first order, second order, third order. So that it goes in this form of increasing. So the poles at origin means they are the zeroth order, right? So zeroth order, first order, second order, third order. This is the zeroth order comes first row, first order, second, so second order, third. So it goes so on. So that is what the small to large. So that is your ascending order. Ascending order is small to big. So for the slope measurement, which is your step 4, these two things are needed. The one is the poles and zeros contribute a slope of plus or minus 20, right? Depending on the first order, or second order means plus or minus 40. Then the order in which we write these terms. Zeroth order comes first order, second order, and so on. So now we come to this. We call this as the slope measurement table in your Bode plot. So we have the slope measurement table, and these are the columns for the slope measurement table. So you have the term corner frequencies, slope, and change in slope. So if you see, first I'm writing from our given G of S, from the given question, I'm writing the 0.75 upon S. So that is the pole at my origin, right? So that is the pole at my origin, and then I am writing my first order pole. Then I am writing my second order pole. So this is the order in which I write my poles in this slope measurement table. And this is very what do you call it? This rule sets have to be followed for all. If you have a pole and zero at origin, so both you have, then you can write either pole or zero. In that case, it doesn't matter. But and if you have two first order, if you have a first order pole and a first order zero, you can write either first order pole or first order zero. So I'll show you, but you have to keep that consistency throughout. So let us do. No, I will come to that in the next set of problems where we see both the poles and the zeros are available for the Bode plot. So next, we have a column is our corner frequency. So this corner frequencies are available to us. So for the zero of first order, my corner frequency is 1 by zero point 0.2, which is 5. And for the second order system, my frequency was 10. So this is known to us. And now I come to my third column. So a pole at origin, a first pole contributes a slope of minus 20, and a second order pole contributes a slope of minus 40. And the zero of first order contributes a pole of slope of plus 20. So that is my third column, and the change of slope is my fourth column. So let's do the step 5. So once you compute these slopes, and now the step 5 is the most important step. That is your gain magnitude computation, because these are the gain values. The gain values are the terms that are going to get plotted on the Bode plot. So how does this Bode plot numerical end with? So you need to plot these Bode plot on a graphical sketch, and you need to plot both the magnitude and your phase response. So if you see here, these are the range corner frequencies that we have fixed: 0.5, 5, 10, and 20, including the lower and the upper bound frequencies. So now I am going to do the change in slope. So the change in slope is something I have written from the previous, right? From the previous, I'm writing this change in slope from the previous table, and I'm writing that as dash dash 0 minus 40. So if you see this arrangement here in step 5, there is something there is a shift in the change in slope. If you write this, there is a shift in the change in slope. So I'm writing it in this manner, right? So this is 0 dash 0 minus 40. Okay, so this shift, it has to be like this, but now with the shift it is written as dash dash 0 and minus 40. So I am writing this in this manner. So this change in slope here is shifted in one place. It's shifted by one place, and this represents a change from my omega 1 to omega 2, and here the change represents from omega 2 to omega h. And this is how I'm using the change in slope in step 5. So if you see the table, so why I didn't mention this change in slope is, if you see this table, if you go back to the previous slide, your table says something like this: dash 0 minus 40. But in this case, I'm shifting it one place down, so I get it as dash dash 0 minus 40. And then I'm using it. Understood? So this is one thing you have to be very careful when you write this, because the mapping of these corner frequencies to these slopes are very, very important for measuring the gain magnitude. If you do this mapping wrong, all the gain values you get will be not proper, and then your Bode plot will also be not correct. So to avoid that, please make sure that you follow this one shift down for mapping the slopes, change in slopes to the corner frequency. Now I can do the gain magnitude. Once I've done that mapping of corner frequency and the change in slope, I can come to the formula for my gain magnitude computation. So the formula for my gain magnitude computation is mod of A dB. So omega, so these are the corner frequencies, and this is mapped to this change in slope. And now I want to find what is this A in dB, the gain in dB. So the gain in dB, I'm using two formulas. So for every Bode plot, we are having two formulas for your gain in dB. So the gain 0, 1, that is given by the change of slope. Okay, so this is your gain. This is change of slope, not applicable. Good, because here what it means is I'm seeing these dash here, these two values. I don't have any change of slope associated with these two frequencies, zero point 0.5 and 5. So that is why I can use only this formula. I can use the gain 1 formula. Then for my gain 2 formula, I have the change of slope. So the change of slope exists for my gain 2 formula, and that is given by this formula. The change of slope into logarithm of the second frequency upon first frequency plus a previous. Good. So I have two formulas for computing the gain, and every Bode plot question you need to apply these two formulas. Good. Okay, so this is a very standard. What we have here is a standard numerical on Bode plot. It is a medium level difficulty problem, and we will see one more question, maybe one or two more questions depending on the requirements we will see, and there we will plot a little more. We'll go with little more difficulty level will be slightly higher than this problem. Okay, so for these corner frequencies, we have to find the gain. So I can say, like, for 4 corner frequency, I will have 4 gains: A1, A2, A3, and A4. So my A1 is given by 20 log 0.75 by S. So this is given by 20 log 0.75 by 0.5, 3.5 dB. Good, this is for the first gain. For the second gain, it is 20 log 0.75 by S, that is 0.75 by 5. So the two corner frequencies, the first two corner frequencies, we are using the 0.75 by this. So we are using the first pole, right? The pole at the origin, that is 0.75 by S, is applied to A1 and A2. Now for A3 and A4, we are using the change in slope. So the change in slope is 0, logarithm of omega 2 by omega 1. So this is transition is from 5 to 10. So 10 upon 5 plus the previous slope is A2. So the previous gain is A2, which is minus 16.5. So as you can see here, it means that for 0 the change is from 5 to 10, and the A previous is A2, and then I can compute my A3. Then for my A4, the change in slope is minus 40, logarithm of 20 divided by 10 plus A previous will be, for A4 it will be A3, and A3 is this value, whatever this value, what we are getting, minus 16.5. So I am putting that A3 to be minus 16.5. So I get these four values: 3.5, minus 16.5, minus 16.5, and minus 28.5. So this is how you compute the gain for Bode plot. So we have done all 4 gains. Good. A very standard question. Every standard questions are going to be like this. So you can even refer other books. You can see the same. But there are certain questions where you have multiple poles and zeros, and there how you arrange this order, how you come up with the corner frequency. So maybe one more numerical is needed in this. We will see that also in the next class. So next, step 6. So we have done the gain magnitude computation. Now we are doing the phase computation. So the phase computation, how do you do the phase computation? I'm writing the G of S as it is from the question. Then I'm putting in the substitution. My S is equal to J omega, right? So the G of S is equal to 0.75 into 1 plus 0.2 J omega divided by J omega into 1 plus 0.6 J omega plus 0.01 J omega square. Good. I'm putting that substitution and then I'm simplifying it. And now here's the thing. For my phase, what we need to do is, the phase is given by the tangent. So the formula for the phase is tan inverse y by x. You know that tan of phase is equal to y by x. So in this case, the y is the imaginary component and x is the real component. So the phase of 1 plus 0.2 j is 0.2 omega by 1, and the phase of j omega is 90, because it is phase of phase of just j omega. I'm writing it as 90, and the phase of 1 plus 0.16, again it is the real divided by imaginary. So, sorry, imaginary divided, tan inverse of imaginary divided by real. The imaginary is 0.16 omega divided by 1 minus zero point 0 omega. So, a pole of phase is a negative. The sign is negative and positive. Good. So, for the phase, the phase of pole is negative and the phase of your zero is positive. Alright, so now, which means I'm putting the signs now. For my 0, I'm putting positive, and for my poles, I'm putting it as negative. Good. So now I can write the final phase equation. And steps is, after doing the substitution, S is equal to J omega, and then simplifying it and then taking the tan inverse of imaginary by real, then applying the sign of positive for zeros and negative for poles, I get my phase response equation to be in this manner. Tan inverse of 0.2 omega minus 90 minus tan inverse of 0.16 omega divided by 1 minus 0.01 omega square. Alright, so this is my poles and that is my zeros, and you can use the scientific calculator, but I have used Scilab. I have used the programming platform Scilab, which is an open source platform, and I have computed the phase response here. So this is the small tiny bit of code that does the calculations for me, and just to match, just to do that the tan inverse, because of the arc tangent limitation, whenever you get arc tangent values to be negative, you need to add up 180. So that is what I have done there. Good. So now let's see the plot. How do we plot this on your Bode? So 0.1, 1, 10, 100. So if you see the divisions, it is all multiples of 10. So 0.1 into 10 is 1, 1 into 10 is 10, 10 into 10 is 100, and the next division will be 100 into 10,000, 10,000, 1 lakh. So you see this, you see each grid represents multiple of 10. So which means I can represent, in my frequency, I can represent hertz to megahertz in the same graph. I can do that. So that is the advantage of using the logarithmic graph. You can plot a wide variation. You can show a large scale of range in the same graph. Alright. So now I'm going to, so once that is the x-axis, and now I have to plot my magnitude and I have to plot my phase on the same log graphs. So you need to plot it on the same graph, and why you are doing that is because you want to compute the phase margin and your gain margin. So your phase margin and the gain margin can be computed only if you draw if you draw these two graphs on top of each other, which means the magnitude plot should be on the top and the phase plot should be on the bottom. So they have to be aligned in such a way that we will be able to map your this phase margin and gain margin on this graphs. So the same x-axis must be applicable for both the phase and your magnitude plot. So that is what I'm going to show you. So in your exams, you will be given a logarithmic paper graph sheets in this manner. And then in my y-axis, I have drawn the magnitude dB values. And then I'm starting to plot. So I have my 4 values, right? So they are 3.5 minus 16.5 minus 16.5. And at the next value was at 20. So the corner frequencies were 0.5, 5, and up to 50. I think that was for the corner frequency, right? So at 20, right? The corner frequency. So I'm taking these. So 3.5 minus 16.5 minus 16.5 and minus 28.5. And then I am just connecting these lines. Just as simple as it. And now you can see that every transition. So at each corner frequency, there is a change of slope. So first is at minus 20, then it becomes 0 dB, and then it is again at minus 40 dB. So this is how your transition slope works. And this is the Bode plot. So this is a very simple, because we have computed only 4 gain values, 4 magnitudes, gain magnitudes. You just have to plot these 4 values and then draw a connecting line between these 4 values. And now on my right hand side, I am doing the y-axis for my phase. So depending on the phase values, I've started from minus 180. So this range, the scale for this y-axis in terms of gain and phase can be slightly tuned to match the table that you get. So every time you may get a table of values, and these table of values have all the values have to be mapped to this scale. So what I'm telling is here I've done the ranges from minus 180 to 100 because I feel that all the face values can be incorporated from that minus 180 to 100. But suppose I'm having from values from just say minus 100 to 100, then I don't have to start from minus 180 because I don't have any value between minus 180 to minus 100. So you see the minimum and the maximum and you fix that range. So in that case, I can keep my minimum to be minus. I can start it from minus 100 and I can go till 100 if I don't have any values between minus 180 to minus 100. So that range is something you have to fix for yourself. But in this program or in this question, I have fixed it from minus 180 to 100. Even that is too much because all my values are in the range minus 180 to minus 40. I can only have that minus 180 to minus 40, and then I can plot all the values from the table. I have plotted it, and then I am drawing a connecting line to this. And for the face, so you don't have to have a sharp connecting line. Your line can be as smooth as possible because the slopes are not very. The slopes are it's a curving slope. You don't have to have a sharp slope as in the magnitude. For magnitude, you have 20, 0, and minus 20. These are the slopes that define. So that way we have to draw a slope with a scale. And for face normally, because even when you see, we have many points. That is why it comes in that curve shape. But yeah, this is how you draw in the exam. Now, your face margin. So in the question, it is also told us that we have to find my face margin and gain margin. So the face margin is something that is given by this 180 plus face when gain dB is 0. So this is the formula. So you see, when the gain is at 0 dB, so what is the value of that? So I get the value to be somewhat, the faces gain as 0 to be what? 88, minus 88. So I'm getting that value to be minus 88, and 180 minus 88 is 92. And my gain margin is given by minus gain at frequency when phase is minus 180. So when phase is equal to 180 degree, so not minus 180, just 180 degree, what is the gain? So if I see here, in this graph, I cannot compute, right? Because there is no meeting point. There, I'm not seeing any 180, and I can say that it is not computable from this graph. So the gain margin is not computable, but the phase margin is computable. And this is the Bode plot on the same question. I did it on my Scilab, and you can see the Bode plot of the magnitude and the phase. And this is how you have to plot it in your graph. So you have to plot one on the alignment is the x-axis is the common. So the x-axis is common for the phase and magnitude, and you plot the magnitude on top of the phase just for computing the phase margin and the gain margin. So what is your phase margin? The phase margin is equal to 180 plus phase at when gain is equal to 0. Right, so when gain is 0, what is the phase? And that is your phase margin. And for gain margin, the formula is minus G when my phase is 180 degree. Good. So we'll practice more on this parameters of phase margin, gain margin, phase crossover frequency, and gain crossover frequency in the next class. So for this class, I think the Bode plot, what is Bode plot? What are the steps needed for plotting the Bode plot? And what is the standard rules? Those 5 to 6 steps that we have seen, that is applicable for all the Bode plot questions. So that should be clear with this lecture. So I'll see you with more on Bode plot in the next class. Thank you.